This video will illustrate the methodology required to integrate using trigonometric identities where you have powers or products of tangents and secants. Formally, this is step 4C. When you have tangents and secant powers, this includes functions integrals that would be of the form any power of tangent or any power of secant that is even, or any products of tangent with secant. Now, typically what you do in a situation like this is as long as these functions are in non-standard form, meaning you don't have secant power 2, you don't have tangent power 1, that you can use the Pythagoras theorem identity that secant squared is the same as 1 plus tan squared. This only replaces for even powers of either tangent or secant. The problem then becomes how you can convert the question into a form that you can identify, a form that you can use substitution on with a function differential relationship. And so if you had, for example, something like this, determine the integral of tangent power 3 times secant power 3. Step 1, you can't do this as a power of angle theta because there are tangents and secants present, trigonometric functions are present. Step 2, you look for a function differential relationship. Derivative of tangent is secant power 2, not secant power 3. Derivative of secant is secant power 1, which you could borrow out of here, times tangent power 1, not tangent power 3. And so what you need to do is, if I break this question, either my secants into secant power 2 and secant power 1, that is not going to help because secant power 1 is not the differential of tangent. But if I break tangent power 3 into tangent squared and tangent power 1, remember that tangent power 1 is related. It is in the derivative of the secant function. And so this is the one that you want to replace. And if I replace that with tan squared times tangent power 1, and you replace inside the cubic function for that tan squared, replace that with secant squared minus 1. I'm writing the tangent function on the end. Notice we have only a whole bunch of secant functions with a single tangent. When I multiply this out, secant power 5 minus secant power 3 times single tangent times d theta. The derivative of secant is secant times tangent. So if I can factor out a single secant out of this bracket so that I'm left with a secant power 4 and a secant power 2, I've removed one of the secants from each. Notice that I am left with the differential of that statement, the differential of secant on the end, secant theta tan theta. So now I can use simple substitution. So the method here was just to replace, and then you start over. You start over at step 1. But is this a power of theta? The answer is no. Step 2, do I see a function derivative? The answer is yes. If I let u be secant theta, the differential of any secant theta is the product. Secant theta tan theta d theta, which is exactly what is written here. So after one substitution, secant power 4 becomes u power 4. Secant power 2 becomes u power 2. Secant theta tan theta d theta is entirely replaced with du. And we end up with, after substitution, we start over at the beginning of the process. Is this a series of powers of u? The answer is yes. And we can go right to the answer. Integral of u to the 4th is 1/5 u to the 5th. Integral u cubed is 1/3 u cubed plus c. And if we undo the substitution and go back to the original variable, u is secant theta, so this is 1/5 secant to the 5th theta minus 1/3 secant cubed theta plus c. Notice you get the familiar pattern where you see a trigonometric function that is repeated, differing by powers of 2. That is, whenever you use the Pythagoras theorem identities, this is often the type of function that you end up with. The key here is that when you do this substitution, you want to get either, like we did here, any power of secant with its differential, secant theta tan theta, both power 1, or alternatively, you're looking for any power of tangent times its differential, secant specifically power 2. So this is how you have to choose. You have to choose to break the original function whose powers of tangent and secant might be even, might be odd. You can break every power of secant. You can take a secant out of it, but you got to make sure you've got a tangent power 1 on the outside. If you can break any of your even powers of secant into squares, you'll have one of them could be used as the differential of tangent function. So there is some creativity involved in choosing which of these two patterns you're going to get. Usually you only get one or the other, but occasionally you can get both. Because remember, secant power 2 times tangent power 1 would be equivalent to this form up here with secant power 1, and tangent. So there are cases where you'll get the same either direction, but these are the patterns that you are looking for.